Hello and welcome back to Complex Analysis. This is part 23 of the series, and here we will finally talk about Cauchy's integral theorem. However, of course you already know, before we do this, I really want to thank all the nice people who support this channel on Steady via PayPal or by other means. Now indeed, this famous theorem we call in short Cauchy's theorem is a generalization from the result from the last video. Please recall, this was Gauss's theorem, which holds in general for a holomorphic function. Hence, the only thing we need is that f is holomorphic and defined on an open set D. Then we can just look at a triangle that lies completely in the set D. So in particular, the whole inside of the triangle has also to lie in D. And then we can say something about the closed contour integral of f. To be precise, it should be the contour integral along the boundary of this triangle. And now you know, in the last video we have proven that under this assumption this integral has to be 0. Again, please remember here, the only two assumptions we need is that the function is holomorphic and that the inside of the triangle lies completely in the domain D. However, at this point you should immediately see, because we have this result for all possible triangles, we can also show it for other shapes. So for example, it's no problem at all to show it for squares, rectangles, and even for all tetragons. We see this because every tetragon can be split up into two triangles. And then of course, the contour integral is calculated along the curve given by the boundary of the shape. Moreover, we know under the assumption that the whole tetragon lies inside the domain D, we can apply Gauss's theorem twice. Hence, you should remember, also these closed contour integrals are always 0 under two assumptions. First, the inner part of the shape has to lie completely in the domain D, and second, the function should be holomorphic. However, at this point you now should see we can generalize this result to all polygons. Simply because we are able to form a polygon out of finitely many triangles. So in other words, this is a really nice result we immediately get from Gauss's theorem. Of course, the only thing we need here is that the inner part of the polygon lies completely in D. And then we just apply Gauss's theorem finitely many times to get the result here. So you see, this is immediately a nice generalization we get here, but you also see we can't say anything about a disk. More precisely, if the curve is a circle, we cannot conclude that the curve integral is also 0 yet. Indeed, now with Cauchy's theorem, we can conclude that this curve integral is 0 for a lot of closed curves. Therefore, the next theorem we formulate here is indeed a special version for Cauchy's theorem. I say it's special because it's formulated for a function where the domain is a disk. This makes the whole formulation simpler because it guarantees that the whole inside of a curve lies in a domain. However, of course, the other assumption that we need a holomorphic function is still given. Now, that D is a disk means we can write that D is equal to an epsilon ball. In other words, we find a middle point Z0 and the radius epsilon. Of course, here we can also consider cases where epsilon is really large. Simply because here only the shape of the domain is important for us. It guarantees that we don't have holes in the domain. Okay, so this is what you can remember in this formulation. The domain should be chosen as an open disk. Moreover, then of course we choose gamma as a closed curve inside D. In other words, it could be any curve for which we have defined the contour integral. And in fact, from this we can conclude that the contour integral has to be 0. Hence, you should see, for this special domain, this generalizes the result we had above. Because here, the contour integral is 0 for every possible shape the curve gamma can take, even if it's not a polygon. So for example, also a circle inside the domain here would work. Okay, now of course, you want to ask about the proof of this nice statement here. And in fact, it turns out here that all the ideas we need for the proof we have already discussed in the last 2 videos. More concretely, we will show that an antiderivative of f exists. There, please recall, if we have an antiderivative, then we already know that the contour integral along closed curves is 0. Hence, we see this is the only thing we need to prove here. Moreover, you also already know from the proof of part 21 that a good candidate for an antiderivative is given by a contour integral. The only thing one has to do is to choose a path gamma z which connects the fixed point z0 to an arbitrary point z. However, now in this proof here, it's really important that we choose straight lines to connect the 2 points. In particular, the path gamma z should be given exactly in this way here. This means for another point z tilde here, the path should look similarly. So one thing you should immediately note here is, if we choose the curve like this, it's guaranteed that this path lies completely inside the disk. And of course, this is an important part of the proof. Moreover, also the connection line here between z and z tilde lies in our disk D. In particular, we recognize this is a closed curve given by a polygon inside D. Therefore, we can apply what we have discussed above, namely that the contour integral along this closed curve here is 0. So we only have to express this polygon curve with the curves gamma that are given. Indeed, this is not hard to see, it's gamma z tilde plus gamma z inverse plus the connection line gamma z z tilde also inversed. And of course, this helps now because we can split this integral up into 3 integrals. Or more precisely, we can use these 3 integrals to show that capital F is an antiderivative of lowercase f. However, there I don't have to show you the details because we already have done this in part 21. So maybe let's quickly go through the general idea here. So we consider the difference quotient here minus f of z. And with the absolute value we can do estimates, and in the end we want to show that the whole thing goes to 0 when z tilde goes to z. Then we simply put in the definition for capital F of z tilde and f of z. And then we see we have the difference here between 2 contour integrals. And then, using the fact above, we see we can substitute this difference simply with 1 contour integral along the connection line here. This is what we do, and we also write the third part here as a contour integral. Hence, you see, at this point we have used our former result known as Gauss's theorem. Okay, and usually here at this point you know we use our standard estimate with the length of the curve gamma. And then we have the nice result that we can cancel this absolute value here with the length of our curve. And then it's not hard to see that the remaining maximum here goes to 0 when z tilde goes to z. So simply by continuity, we know that the values also get closer and closer. So in summary, we get the result that the difference quotient goes to f of z. Or to say it in other words, the thing we wanted to show, that capital F is an antiderivative of lowercase f, is now shown. Now, of course, this works for every point z in the domain, which means f has an antiderivative defined on the whole domain D. However, for this case we have already proven the fact that every contour integral along a closed curve is 0. And indeed, this closes our proof of Cauchy's theorem. However, at the moment it only works if we can shrink the domain of f to an open disk D. In particular, this is possible if we have an entire function, where the domain is the whole complex plane C. Okay, with this I think it's good enough for today. Thanks for listening and see you next time. Bye!